Enzymes are what we call biological catalysts, and they're incredible. By a catalyst, what we mean is that it can speed up a reaction without getting used up in the process, so it can keep doing this over and over and over again. We call the molecules that the enzymes actually bind to and change substrates. And unlike other types of catalysts that are more generic, like metals, enzymes are very specific because they're making specific interactions with the substrates that they're binding. And in this way, they're able to have different enzymes that are specialized for acting on different substrates, thus providing you with specificity in addition to having that awesome speediness. And when we're talking about speeding things up, this can be dramatic. So we have this value that we'll talk about when we get to enzyme kinetics. That's the kcat, or the turnover number. And that's how many times a single copy of an enzyme can basically turn over or process a molecule and change the molecule. And typically these are going to be 100 to 1,000 times per second. And the rate at which a reaction will happen in the presence of an enzyme can be thousands to even millions and tens of millions of times faster than would happen on its own. So one of the most important enzymes in our body is one of the fastest, this carbonic anhydrase. What it is doing is it's actually helping act as a pH buffer that's keeping your pH stable, and that's helping with your hemoglobin and things. And so enzymes vary dramatically in terms of their how fast they can go, and they vary dramatically in terms of what they do. So enzymes are crucial to metabolism, and we'll talk about metabolism, the making and breaking of molecules. Each of the steps of metabolism is basically catalyzed or sped up by a different enzyme. This allows us to break down different molecules, and we can use different enzymes to take the molecules through different pathways. We can use enzymes in the lab when we want to do things like cut DNA and paste them places. We can make copies of DNA both in the lab and in our bodies. We can phosphorylate proteins. We can make proteins. And so most of our enzymes are going to be proteins, but the ribosome is actually made up of protein and RNA, and the RNA is actually going to be doing the catalytic roles. And so RNA can act as an enzyme too. And if you have just RNA acting as an enzyme, we often call that a ribozyme. So enzymes can do a lot of different things, and different enzymes will do different things depending on their structure, which depends on their amino acid makeup. But although they do these various things, we can kind of clump them into a variety of classes. And so we'll get to these later, the different classes we can clump enzymes into. And although they do different things, they often use a bunch of the similar strategies. So just like in OChem, how you might have seen that OChem is a lot more fun if you focus on tracking the electrons and thinking about the mechanisms in terms of logicking your way through them and seeing the similarities rather than trying to just memorize things. Similarly, we're going to want to have that same mindset when we approach biochemistry. We'll see that enzymes use a lot of the same mechanisms to do similar things with different molecules, or sometimes they'll use different strategies to do the same thing with one molecule. And that all gets back to differences in amino acid composition, as well as sometimes the enzymes are actually going to be using helpers, which we're going to call cofactors. So enzymes are awesome, but it's also important to know their limitations. And so enzymes can speed up a reaction. They can make it faster to reach equilibrium, but they can't change that equilibrium. And so what enzymes do is they lower what we call the activation barrier. So if you imagine a rainbow, that you have a pot of gold on one side of the rainbow, and so you really want to get to that pot of gold, but you have to go over the rainbow in order to get there. Enzymes kind of provide an alternate route, a shorter rainbow, if you like, that'll allow you to get to that pot of gold more quickly. But they can't change the favorability of that pot of gold. And they make it easier to go back the other direction because enzymes, by lowering the barrier of the rainbow, by lowering that, now you're able to go back and forth more easily. And so enzymes are going to speed up the forward direction and the reverse direction at the same rate. And how they're going to do this is lower this basically the really uncomfy spot. So if you think about trying to snap a stick, when you're in that state, when you're really like close to breaking that stick, it's going to be really uncomfy, and you can kind of go either way equally well. That's going to be your transition state. And so the transition state is this fleeting moment. We can't even isolate it, but we know it has to exist because we can go on either side of it. And that's what enzymes are going to stabilize. So enzymes bind to that transition state. They stabilize that really, really, really unstable, uncomfortable conformation and make it easier then to get to the top of the rainbow. But then once you're at the top of the rainbow, you can basically fall other side. And what that depends on is going to be things like the thermodynamic favorability. And so let's talk a little about thermodynamics. What we're looking at here is kind of a fun version of what we call a reactant coordinate diagram or a free energy diagram. So when we talk about an enzyme catalyzed reaction, we often are going to use this notation where we have E is our enzyme, S is our substrate. The enzyme binds the substrate, and you get this ES, this enzyme substrate complex. And then the enzyme converts the substrate into the product. Then so you get this EP, and then those get released, and you get this E plus P. And often we abbreviate it to just thinking about E plus S gives us ES, gives us E plus P. The enzyme can't make the reaction happen. That couldn't happen without the enzyme, but it makes it much more likely, and it basically facilitates the process. So when we're looking at one of these diagrams, on the x-axis, we're going to have the reaction coordinate or progress of the reaction. So this isn't a linear time scale. It's just saying this is kind of the overall progress of the reaction. You can see those different forms we were talking about. So our enzyme plus our substrate, our enzyme substrate complex, our enzyme product complex, and our enzyme plus our products. And then you'll see this double dagger. This double dagger is indicating a transition state. And so the transition state is going to be that really uncomfy moment where you have partial bonds forming and partial bonds breaking, and you're right at that point at which you can really go either way equally easily. And enzymes make it easier to get to that point at which you can go either way equally easily. And which way you're going to stay is going to depend on the thermodynamic favorability, which gets us to thinking about G and delta G. So on our y-axis, we have energy, so that's our G. And then we want to look at the difference in energy between the different parts of the diagram. So if we compare E plus S, so our enzyme plus our substrate, to E plus P, our enzyme plus our product, well, that's going to give us our overall delta G. That overall delta G is going to tell us about the overall favorability of the reaction. So which way are you going to end up? On which side of the rainbow, if we were to let you reach equilibrium, where would the equilibrium lie? If the products have a lower energy, you're going to end up with more products. And if the reactants have a lower energy, you're going to end up with more reactants. If the products are higher than the reactions, we say this is endergonic, it has a positive delta G. If the products are lower than the reactants, we say it's exergonic, it has a negative delta G. And that's thermodynamically favorable. But even if you have an endergonic reaction, enzymes can help you get to having products made in the first place by lowering the activation barrier. And then if you're able to siphon away the products, you can use concentrations in order to drive forward this progress. And so we'll see when we talk about metabolism, we'll have basically chains of reactions where the products from one reaction, which might be an endergonic reaction, are going to then be used for something else. And so then they're going to be able to drive things that way. So when we're looking at one of these, we're showing a couple different lines. One is the uncatalyzed, and then the blue is the catalyzed. In both cases, we have a transition state, because in both cases, you have to go through that really uncomfy spot in order to get to the other side. But in the case of our enzyme, that really uncomfy state, so when we think about uncomfy, we have a high energy, we have a high free energy. And when we're catalyzed, we're more comfy. Well, now we have a lower free energy. And we can see that there's a lower energy when we have an enzyme catalyzed reaction. And so there are different ways that you can see this represented. And so sometimes you'll see like this delta G double dagger cat. And so that's telling you that this is the amount of what we call the activation barrier for the enzyme catalyzed reaction versus the activation barrier for the reaction in the absence of an enzyme. The activation energy is going to be the largest difference in free energy between two steps. And so when we think about here, if we have our reactants and then we have this transition state, we only have a single one here, but things with enzymes can get more complicated because things are often going to have an alternate route in the presence of an enzyme. So we often simplify things by looking at this, but we are going to see something that's more complicated like this. And we'll see that a lot of times enzymes do these multi-step reactions where you're going to have multiple transition states and multiple intermediates. So we need to discuss for a second the difference between an intermediate and a transition state. An intermediate is going to have full bonds. It's going to be at least theoretically isolatable. And a transition state is going to have partial bonds, and it is not actually isolatable, but it does have to happen because you have to get from one side of it to the other side of it. These involve like partial bonds forming and breaking and partial charges. And so they're often really, really awkward. And the enzyme is going to be able to kind of do things like provide opposite charges and things like this to help stabilize them. The transition states are typically indicated by these double dagger symbol, and the transition state will often be shown in brackets. Quick word of caution though, sometimes you'll see that intermediates are shown in brackets, but typically you'll only see that double dagger in the case of a transition state, which often isn't actually shown. So to show you an example and to try to help directly see what's a transition state and what's an intermediate, we need to review our arrow pushing. So remember the rules for arrow pushing from organic chemistry. Your arrows are going to start at a lone pair of electrons or a pi bond, so like a double bond or triple bond, and they're going to always go from nucleophile to electrophile. So remember that our nucleophile, they are the things with typically a lone pair of electrons that is going to seek out some positivity. They want someone to share their electrons with. So they're going to look for protons, and protons can be found in the nucleus, hence the word nucleophiles. They love the nucleus because that's where the protons are. They're going to seek out something that wants to share some positivity. So electrophiles, basically, they want more electrons. And so these are what the nucleophile is going to attack. By attacking the electrophile, well, now you can do things like form new bonds, form double bonds, or deprotonate, all this good stuff. It starts with the nucleophile attacking the electrophile, and this is what you're going to represent in your arrow pushing diagrams. In terms of the nucleophiles that we'll see in biochemistry, these are often going to be things like hydroxyl groups. Deprotonated is especially strong. We'll see amine groups. We'll see like histidines and imidazole ring. We'll see double and triple bonds. In terms of our electrophiles, we'll be dealing with things like the C and carbonyls. This is going to be a really big one. So the oxygen is going to be pulling away from that carbon, making the carbon partly positive. Another common one is going to be the P in phosphates. And so similarly to how the C was partly positive because the oxygen is pulling away electrons from it, the phosphates in these phosphate groups are going to be partly positive because the oxygens are pulling electrons away from it. And we'll also see things like an ammonium cation serve as our electrophiles. In terms of the reactions that we're actually going to see, so remember you start from your nucleophile, you go to the electrophile, and then what happens is going to depend on the reaction mechanism. So you might kick off the leaving group, get a new, like a substitution reaction. You might get an elimination reaction. You might just like steal a proton. All of these can happen, and this is just happening from going from a nucleophile to an electrophile. So for example, if we had a nucleophilic addition and elimination to a carbonyl group, which we're going to see over and over and over again, what we would see is that basically we have a nucleophile. Remember, often a nucleophile is going to be a lone pair and an oxygen or a nitrogen, and our electrophile is often going to be a carbonyl carbon. We draw our arrow from our nucleophile to the electrophile. So in this case, our nucleophile is going to be the oxygen on this water, and our electrophile is going to be this carbonyl carbon. When we have them attack, basically what's going to happen is ultimately we're going to form a tetrahedral intermediate. So an intermediate, we have actual bonds here. But in order to get that to that point, we first had to have a partial bond being formed and this partial bond being broken. So this is our transition states. This is what we put in brackets with the double dagger. This is what the enzyme is going to be the most stabilizing to and provide the most help for. Additionally, we would also have another transition state on this side of the intermediate as we go from having these bonds formed to then breaking off this other bond. In this example, they're only showing this transition state because this is going to be the slower one, the rate determining step. But you are also going to have a transition state on the other side. And so you're going to have two peaks on either side of that valley representing where the valley is your intermediate and the peaks on either side are going to be your transition states. But in order to even get to this transition state, we have to make it more likely. And so we can do this in a couple of ways. And so we're going to look at how acid and base catalysis can either strengthen the nucleophile or strengthen the electrophile, and how other things like metals can help stabilize the charge on the transition state. And all these enzymes can kind of all provide interactions with this transition state that are going to help lower the energy required to actually get there. And then once it gets there, which way it goes is going to depend on the overall thermodynamic favorability of the reaction, which is something that that enzyme can't change. But by doing it in little steps where each step isn't quite as bad, it can make it easier for the reaction to happen. And later in the course, we'll look at how by kind of controlling the concentrations of the products and the reactants, we can favor one direction or the other. Transition states are going to be represented by the peaks of a free energy diagram. And then your troughs, so the bottoms, the valleys, are going to be the intermediates. So you can see that the intermediates are more stable than those places where you have those partial bonds and you're in the process of breaking and making things. And so you'll see that each of these is going to have kind of a difference in energy that it has to go from one step to the next, to get to a transition state from the intermediate on the other side. However, the biggest one that you're going to have to go through, the biggest step is going to correspond to the activation barrier. The energy for that is going to be your activation energy. And that's the energy that's going to be the slowest step, is going to be that step that has that largest activation energy because you're kind of held up at that step before you can get to the other steps. It doesn't have to be the first step, though. It can be a later step. But if you have a red light 3 blocks down, you're still going to be tied up before that red light because you're going to be limited by that red light. Conversely, the one with the lowest delta G double dagger is going to be the fastest because that step is the easiest. So the magnitude of the delta G is going to tell us about how easy or hard that step is and thus how fast or slow it is. And so enzymes can make it easier to get to that point at which you have your equilibrium reached because you are lowering the activation barrier. But if your reaction is endergonic overall, if you're not doing anything to make it more favorable by, say, using the products so that the concentrations stay low, well, then what's going to happen is you're actually going to make it easier to reach that equilibrium in which you still have more of the reactants. And so we'll talk more when we get to thermodynamics about some of that sort of thing. But for now, some of the key things to remember are that the delta G, so the difference between the products and the reactants and their energy, is going to tell you about thermodynamic favorability. It's going to tell you, like, if we were to allow these to reach their happy place, their equilibrium, would you have more products or would you have more reactants? If you had a positive delta G, you would have more reactants. But if you had a negative delta G, you would have more products. Basically, you have your pot of gold is going to be on your product side versus the pot of gold on the reactant side. You're always going to end up where the pot of gold is if you were to allow things to reach equilibrium, but the enzyme is going to make it easier to get from one side of the rainbow to another. And it's going to do this by making the top of the rainbow shorter, basically. It's going to stabilize the transition state, the top of the rainbow, and how it's going to do this is various ways, but it basically can hug onto that transition state and have those intermolecular force interactions that are kind of going to be counterbalancing the negative aspects of that transition state and thereby lowering the energy that is actually required to get over that hump. No matter how complicated one of these diagrams looks like, note that in a reaction coordinate diagram, the peaks are going to be the transition states, the troughs are going to be the intermediates. You look to overall the reactants versus the products in order to know the overall favorability, And you look to the largest difference between two of the steps between an intermediate and a transition state in order to know what is going to be the slowest rate determining step. And the free energy difference for that, the delta G for that, is going to be your activation energy. And enzymes can lower the activation energy that's needed by stabilizing the transition state and lowering the energy of that transition state. So sometimes you'll see it called like activation barrier, activation energy. It's the same idea. There's a pot of gold on the other side of the rainbow, but you got to get up and go and trek over that rainbow to get there. And the enzyme can make it easier for you to get there. But it also makes it easier for you to go back the other way. And so then you have to go to thermodynamics to think about which way things would stay. Note that you want enzymes to lower the transition state, but anytime you form favorable interactions with something, you're going to lower the free energy. This includes when the enzyme binds to the substrate. So when the enzyme binds to the substrate, you get a dip in the energy, and so this is favorable, which makes it favorable to bind. But if you make it too comfy here, what you're doing when you're lowering this energy is you're raising the actual activation barrier because you're lowering the intermediate before this step. And so you don't want the enzyme to bind too tightly to the substrate. You want the enzyme to bind most tightly to the transition state. Transition state analogs are often used as pharmaceutical drugs to like inhibit enzymes. If you want to have the enzyme bind to something really tightly, you want to mimic the transition state because that's what the enzyme binds to most tightly. You wouldn't want it to bind too tightly to the substrate or too tightly to the products, or else it won't release the products. And so the transition state is what the enzyme kind of is best at binding. But it should be noted that it's not just a lock and key type of thing. Instead, it's an induced fit mechanism. And so the active site is where the enzyme binds onto that substrate and then changes that substrate into a product. But the enzyme can also release it before it makes the product. And so we'll see when we talk about kinetics that you're actually going to have these binding interactions and the catalysis part, the actual changing of the substrate into a product. Both of those are going to influence the overall rate of the reaction. So we have the enzyme binding to the substrate, dropping the substrate, binding to the substrate, dropping the substrate. And then once it's bound to the substrate, it can turn it into product or it cannot turn it into product. And so we're going to have the speed of how fast it turns the substrate into product. And we're going to have the differences in binding and unbinding and binding and unbinding. And so this is going to be kind of what we call the Km, and this will be the Kcat, and we'll get to that later. But you'll see that these interactions are going to be both directional, and so you have to keep that in mind. And keep in mind that the enzyme is binding to the substrate, transitioning it into the product, and it's going to kind of ease the transition into that transition state. So typically it'll bind to the substrate and then kind of do an induced fit type of thing where it forms these favorable interactions that are most favorable in that most uncomfy state for the substrate. And so what it's going to be doing is kind of like hugging it and molding it as it hugs it and molding it into that transition state. And then at that transition state is where it has the most tight of a hug, the most stabilization. And then that transition state is where you can then go and convert into the product. So don't think lock and key, think induced fit because you've got to get it from the substrate into the transition state, but you've got to bind it to the substrate form. And so you can't look just like the transition state or else you wouldn't bind to the substrate. But because the substrate and the transition state are similar in appearance, we can predict things and design things based on the substrate because we can't see that transition state. We just know the transition state has to exist because we have to get from one side to the other. That transition state could happen in the absence of an enzyme because the enzyme can't make a reaction happen that couldn't happen on its own, but the enzyme is going to make it much more easy to get to that transition state by that hug and mold, that induced fit. And then it's going to actually help the enzyme do the chemical catalysis. And we'll see that there are different mechanisms that the enzymes can use to help facilitate the actual chemical conversion. In addition to what we call proximity catalysis, which is basically it's just binding to it, providing that binding energy that'll lower that transition state. And it's also then bringing together the components. So if you have a multi-component reaction, the enzyme is going to make it so that they're closer together. So we can talk about like entropy reduction. And so it's basically bringing these things together and making it easier for the reaction to happen. Kind of like raising the local concentrations and holding things in the right orientation for things to happen. Note that we're going to see several types of graphs when we talk about enzymes. And so now we're talking about these free energy diagrams or reaction coordinate diagrams. Later, we're going to look at how those thermodynamics can actually lead to differences in observed kinetics, and then how the kinetics and thermodynamics interplay. For the kinetics, we're going to be looking at different types of curves. We'll look at reaction progress curves and Michaelis-Menten graphs. So this, though, is going to be the reaction coordinate diagram, and we'll deal with these in future lessons. And the key things to know when looking at these is steps with a large positive delta G are slow. When you see this double dagger, it's indicating a transition state, and those are going to be at the peaks. You'll see that on either side of one of the intermediates, you're going to have a transition state. And the free energy difference associated with the largest difference between one of the intermediates and the transition state is going to be the activation barrier. And enzymes can lower that barrier. Try to answer these following questions. How many intermediates and transition states does each have? Rank them from least to most thermodynamically favorable, and tell me which happens easiest and thus fastest. Okay, let's start with how many intermediates and transition states. They made it kind of easy in these figures because it's like int and TS3 or TS, intermediate and transition state, but you would be able to know based on looking for the troughs. And so each of these is an intermediate, and then each of these is the transition state. And so this one would have 2 intermediates, 3 transition states. This would have 1 intermediate, 2 transition states, and this would have 3 intermediates and 4 transition states. And remember, the intermediates are going to be the kind of like isolatable things. The transition states, that's our tipping point. That's the thing that we really care about. But we can't like actually capture it. Okay, which is the least to most thermodynamically favorable? So remember, what do we need to think about when it comes to thermodynamic favorability? Yeah, we need to think about our overall delta G, the difference between our substrates and our products. And so we need to be looking at the start and at the end. We can ignore everything else that happens in between. So it's kind of hard to tell with these diagrams, but let's say we draw a line over to here, over to here, and over to here. And now we want to see like what would our delta G be? Well, here they're pretty similar, so that wouldn't be that favorable. So this would be R1. How about this one? This one's more favorable than the first one, but is it more favorable than this one? No. So this would be R2, and this would be R3. So the first would be our least thermodynamically favorable, but still favorable slightly because it's got a negative delta G. The second is going to be more favorable, and then the third is going to be the most favorable. So remember, that's telling us if you let them reach equilibrium, we'd expect that we'd have the most products in the case of number 3. But which is going to happen easiest and thus fastest? Now what do we need to consider? Now we need to consider our delta G double dagger. And so if we consider that, well, we've got a big one here. We're up to about 100 kilojoules per mole. For this one, we're a little under 75. This one looks like we're about a little over 75 as well. And so basically what's going to happen easiest is it's going to be 2 and 3, and the hardest is going to be 1 because it's got the highest activation barrier. Be forewarned that coordinate diagrams can get really, really complicated, and don't worry about those. All I need you to do is be able to look at a coordinate diagram, recognize where the intermediates are, where the transition states are, use them to identify if overall the reaction is thermodynamically favorable, and identify what the rate limiting step would be.
So if we look at what would be the rate limiting step here, well, it looks like although TS3 is going to have the highest free energy, it actually looks like it's going to have a smaller activation barrier than getting from this Int3 to this TS4, to this transition state. So remember that enzymes are biological catalysts. They speed up reactions without being used up in the process. And the way that they speed up these reactions is basically by lowering the activation barrier. They can do these in a variety of ways, including making lots of weak interactions with the substrate that are going to help provide the binding energy to offset the cost, and they're going to provide specificity. Sometimes enzymes actually get directly involved in the reaction by forming covalent intermediates, but often it's just going to be non-covalent interactions. And even if it has covalent interactions, the bulk of the power is really coming from that non-covalent stuff. Sometimes enzymes go work with helpers. They have metal ions or they have other organic groups. Remember that substrate is just the name for the thing that the enzyme binds and acts on. The substrate binds to the active site and gets changed into products. The enzyme catalyzes things in both directions, forward and backwards. It can't change the equilibrium. It can only make the reaction get there faster. Sometimes it does these through complicated pathways, but when you're looking at a reaction coordinate diagram, note that the intermediates are going to be the valleys in between the peaks, and then the peaks themselves are going to be the transition state. Remember, transition states we represent with that double dagger. That's kind of the tipping point, and it's so unstable that we can't even see it. We can't even isolate it. And it's that point that the enzyme is going to hug the most, care the most about. So that's where you're going to have the most of those favorable interactions. So enzymes are often going to, the active site's kind of going to look like the transition state, that really uncomfy state. But in order to get there, you have to have a sort of induced fit where the enzyme's kind of changing shape gently around the substrate, providing that binding energy, getting it to that transition state, and helping make that easier to get to.
Next lesson, we'll go to our main catalytic strategies I briefly mentioned. We'll talk more about acid-base catalysis, as well as proximity catalysis, so holding things together, metal catalysis, when those metals get involved, covalent catalysis, when we're actually forming bonds between the enzyme and the substrate that then get broken later. We'll also look at specific examples and talk about how we can classify enzymes based on the kind of strategies they use and the reactions that they catalyze.